Thank you so much for joining. Awesome. Yeah, very well. Yeah, thank you so much for joining, everyone, and especially Michael. It's really great to have you here. It's amazing to have somebody who is expert on the topic because today we are covering the consensus layer data structures, how the beacon node handles all kinds of data, and yeah, it's really great to have Michael here because he's from Lighthouse and he's been working on the three-state database for Lighthouse, so he knows the in and outs um, of the data structures in Beacon and the SSZ and so on. So again, thank you so much for being here. And yeah, the stage is yours. Please share your presentation and go ahead. Yeah.
Thank you, Mario. Yeah, it's a pleasure to be here. Yeah, I'll get started right away. Here we go. Oop, I don't want that. Oops, what did I do? Okay, no, that's good. Yeah, okay, so today we're talking about consensus layer data structures. Actually, can I make this full screen? I feel like... There we go, that's better. Yeah, so consensus layer data structures. As Mario said, I'm from Sigma Prime and I work on the Lighthouse client. I've been working on Lighthouse for about 6 years now, which feels kind of crazy to say out loud, but yeah, it's been a while and I've worked on lots of different things in Lighthouse, but lots of the consensus code and the database stuff has been, yeah, stuff that I've sort of worked on or come up with ideas and then worked on it with other people. So yeah, we're going to go into some of that today. I'm going to cover sort of three main topics. We're going to talk about how beacon state gets represented in memory. And I've got a quick overview of what the beacon state is, just as a refresher. And then we're going to also talk about how beacon states are stored on disk, and that's the tree states work that Mario alluded to. And then we've also got a little short topic on how Lighthouse specifically stores blocks and blobs, mainly on disk. Yeah, so let's start with the in-memory stuff. So the beacon state, just to remind you, is the state that's specific to the consensus layer, and it just includes things that the consensus layer needs. So it's all of the new stuff that was added in Ethereum 2.0 or added during the merge, and none of the stuff like the smart contract state or the account balances or anything like this. And as a result, it means that it's relatively compact. So on Ethereum mainnet, we have maybe, I think it's probably 1.8 million validators now. And the size of the beacon state is pretty much just proportional to those 1.8 million validators. So each validator gets maybe 100 and something bytes in this state where they have their public key, their withdrawal credentials, their activation epoch, their current balance, things like this. And then you just have 1.8 million of them. So it's like, yeah, it's around like, you know, the order of hundreds of megabytes and not like hundreds of gigabytes like the execution state. So specifically, I checked yesterday, and the mainnet state at the head is 250 megabytes, and that's when it's serialized as SSZ, which is SSZ is this encoding format that we use in the consensus layer. It's basically it's a binary format where you can represent any of the data that is in the consensus layer in that format. So you just encode it and you get a string of bytes, and that string of bytes is 250 megabytes for the current mainnet state. So when it comes to storing the state, we want to think about what sort of things we want to do with that state in memory. And there's kind of three main ones that affect our choice of a state representation in memory. The main one that we do is block processing. So this is the act of getting a new block from the network, maybe via Gossip or RPC, and then having to process that block by loading its parent block and the state for the parent block, and then processing the block on top of that state to get a new state. So it's sort of like you have the old state, you get a block, you get the new state, and that's the consensus state transition. So that's an important thing that we have to do. Hashing the state is also something that we have to do. So Ethereum uses this system where we hash the whole state as a binary tree in the case of the consensus layer, or as a Patricia Merkle tree in the case of the execution layer. But in the consensus layer world, it's all binary Merkle trees, and we have to just compute the state root. So we get one singular hash 256 value, which represents the hash of the whole beacon state. So we'd start with the state before block processing, we'd apply the block, we get a new state, and then we compute the state root for that post state and make sure that it matches the state root that was included in the block. Because if it doesn't match, then that means we've probably got a consensus inconsistency with the proposer of the block. And that does happen sometimes when there's a bug, but hopefully not too often. And then the last thing that we want to do with states that's kind of significant is reading and writing them from disk. And this kind of ties into the second topic that we'll cover, which is how we represent state on disk. But our in-memory representation ideally sort of has to be compatible with that, or it has to not mess us up too much. And in the case of Lighthouse, our reading and writing from disk is actually still really slow for our state representation that we use, but I'll go into why that's okay in a little while. But yeah, basically we want to choose a representation that balances these concerns, and we want to keep memory usage low, because we don't want to just throw all this data around in memory and then suddenly the beacon node is using 25 gigabytes of RAM, which is still happens sometimes, unfortunately, but usually it's fixable. So yeah, that's the idea. I'm going to go into a bit of detail about block processing specifically, and how this motivated our choice of state representation. So most of the time on the chain, you've got a very orderly system where we've got the rectangle here is B1, that's a block. And after applying B1, the state of the system is sigma 1. This sigma is the same sigma that sigma prime is named after, the state, which is a nice, cute coincidence. And then we have a new block B2. So this is what I was talking about, where we have the existing state of the system, we have a new block, and we want to apply that block using the state transition to get a new state. So most of the time, that's exactly what happens. Maybe we had sigma 1 in memory, so green is in memory. We apply the block, and then we have the new sigma 2, and we take the existing state, we mutate it when we apply block 2, and then we get a new state, sigma 2, which does mean that sigma 1 is no longer held in memory, because it has been mutated into sigma 2, right? So this is how Lighthouse used to work before 2024. Yeah, I think that's right. So the problem with this is what happens if, you get a reorg or an attempted reorg where suddenly there's a new block that doesn't know about block 2, and it wants to build on the state from block 1. So it wants to build on sigma 1. This would be a cache miss. So you have sigma 2 in memory, but you don't have sigma 1. So then you have to rebuild sigma 1, and this is maybe going to be slow, because you might have to load some data from disk. You might have to redo some block processing to get to that point. And at this point, this was a major source of performance headaches for us in Lighthouse, because we were trying to come up with these heuristics about, well, maybe if it's, if this block is late, then we copy this state rather than moving it, but then the copying itself was slow, so we're sort of paying a performance penalty all the time to account for this scenario that could happen. And you don't know that this is going to happen until after you've already processed B2, so you don't know whether you needed to keep sigma 1 until this happens. And this happens quite a lot on mainnet. I mean, not too much, but it probably happens every day, multiple times every day, because all it takes is one proposer to say propose their block B2 late, and then someone else is going to build B3 to orphan B2 because it was built late and no one saw it and no one voted for it. So it's kind of a low quality block. So this chain it's not bad that we reorg this out. It's probably actually good that we reorg this out. But the beacon node needs to be able to handle these reorgs and needs to be able to quickly process this block so that it's not then late or processed late because of the cache miss. So what we want to do is we kind of want to have our cake and eat it too. We want to have access to lots and lots of beacon states, or at least, you know, a handful, more than one, definitely. But we also want to keep memory usage low. So we don't want to just say, oh, well, each beacon state is 250 megabytes, so I'll just keep 100 of them, because that's going to then use, what, 100 times 250 is like 25 gigabytes of RAM, right? So we don't want to just do the naive thing of like having a million beacon states in memory. So we thought about, well, what if we used something a bit more clever to store them? So there's a paradigm called copy on write, which is where whenever you change a data structure, you copy all of the parts of the data structure that you're changing, change those copies, and then you still have the original data structure fully intact. And this is very popular in functional programming languages, where this concept is called persistent data structures. They're also called immutable data structures or things like this. So, but the idea is that it fits very well with the blockchain paradigm, because you have the old thing, it's immutable, it's got a state root, you know, the old state, it's completely like sort of sealed. And then when you apply a block, you get a new state, and that new state doesn't go and mutate any of the old state. It just makes new parts that reference the old state. So this is sort of what it looks like. The main data structure we use in the consensus layer that's persistent is this. It's a vector with leaves that are the entries of the vector. So v1, v0, v1, v2, etc. along here. But it's a vector represented as a tree because we want to be able to hash. This is a binary Merkle tree even. We want to be able to hash these leaves together to get the internal hash, and then hash all the way up to get the root. So if this list were part of the beacon state, we would have all of the leaves, which would be the values. So these could be like the list of validators as the leaves. And then the internal nodes are going to be hashes of those pairs of children nodes until we get to the root. And then on the beacon state as a whole, we're going to have a whole bunch of these lists. So we'll have the list of validators, the list of balances, the list of something else. And then we'll put those in a binary Merkle tree and hash them up to get the state root. So yeah, this is the main data structure we use. And I've used a sort of Haskell-like syntax here, but that's just to illustrate really that, you know, a tree is either a leaf, which has the hash of the leaf and the value, or it's a node, which has the hash of the node and two children, which are both trees, or this is a kind of special case, it's a zero node. So for the parts of the tree that we haven't added any leaves in yet, we don't actually have to put anything there. We can just know that, okay, there's basically an empty space at this particular height, and we can pre-compute basically the hash of this subtree, and just know that we know the hash of that when we're calculating the hash of its parent. So these zero nodes are just sort of like they're an optimization that just fills in the unexpanded parts of the tree. Okay. Yeah. Does anyone have any questions at this stage? Because I feel like the first time you see this, it's probably a little bit confusing.
Any questions? Feel free to raise your hand or write in the comments.
Oh, I don't think I can actually see the comments, but if there is one,
yeah, I will read it.
Let me know. Okay, cool. I guess I'll keep going, but I can answer some questions at the end. So this is the idea of the immutable or persistent data structure that we use. And this is what it looks like when we apply a mutation. So it's the yellow nodes are the ones that are being updated, and the green ones are the updated versions, and the white ones are the ones that are shared between both versions. So This is, we have a list v0 to v4, and we're pushing a new element v5. And the result of that push is that we create v5 as a leaf node, and then we make a new parent node for v5, which has v4 and v5 as children, which means that we are no longer referring to this previous parent node or this zero node that we're in the old tree. So they're sort of they still exist, but they are no longer referenced in the new tree. And then we need a new parent for that node. So as its left child, it has this new child that we created, but as its right child, we can reuse the right child of this node that already existed. So we get to reuse this zero node and share it between the new tree and the old tree. And then we create a new root as well, which is the same sort of thing, where we have the new right child that we just created, and then we get to reuse the old left child, which includes all of the values v0 to v4, or v0 to v3 at least, that were in the previous tree. So we have this new data structure which shares most of its data with the old one, and just adds a few little nodes in order to represent this update. And this is vastly less memory than if we had copied the whole tree and then added the v5, which is essentially how it behaves, because we get to have both copies. We get to have a full version of the old tree, and we get to have a full version of the new tree, and we can treat those as completely independent values if we want to. But they end up under the hood, they use basically the same amount of memory as v5 would use, or with a little bit of overhead for these extra nodes, which were added. So that's pretty cool. When we implemented this, I was pretty excited. There are some performance differences between this tree representation and like an array that you would usually use to represent a vector. So because it's a tree, most of the operations like get, set, and append are log n, because you have to traverse down to the leaf, where n is either the like maximum length of the list, which is what we use quite a lot in SSZ, or it's the number of things in the list. It's they end up being fairly similar. And yeah, in an array, like a vec in Rust, you can append to the list in O1 amortized time, because most of the time you get to just push into spare capacity, and then sometimes you have to double the capacity of the list. Like that's a very standard thing that vectors do, but we have to pay O log n every time. The one where we win, and this is the main reason to do this, is cloning the data structure. So if you clone an array, you have to iterate through and clone every element. If you clone the tree, then you just copy a reference to the root, and then you have a new tree, which is exactly the same as the old one. And then any mutations that happen on that tree will automatically only update the nodes of the new tree and not touch the old one. So cloning like that is safe, and it's very fast, because we use a reference counted pointer for the root node, and then once we clone that, it's basically free. And then iteration is interesting. They're both ON, so they're both proportional to the number of elements in the list. But in the tree case, the constant factor is quite a lot larger, because you have to do this big tree traversal where you go all the way down to index 0, and then you go sort of up the tree to index 1, and then you go up and down basically a lot, and you have to maintain this stack of nodes that's growing and shrinking and stuff. Whereas in an array, you have all your entries just contiguous in memory, and you just increment a pointer to jump along between them. So in practice, iteration, even though it has the same big O complexity, ends up being quite a bit slower for the tree vector, and it's something that we want to we end up having to avoid doing too much of. So in Lighthouse, the way this is implemented is a library called Millhouse. We implemented this library several years ago, and then sort of went through a process of stabilizing it and getting it merged and getting it tested. And there's fuzzing and there's property tests and stuff to make sure that it's really solid and that it could it could get into the core of the client and replace what we were using before. That replacement went pretty smoothly, I think. And then, yeah, we can fit around 128 beacon states in memory, in a similar amount of RAM to 3 to 4 like full states, which is pretty cool. So our previous state caching system could only keep around 3 or 4 states before it would run out of memory. So we'd have to limit it to three or 4 states. And then the new system, you can say, okay, I'll keep up to 128 states in memory, and that will be a similar amount of RAM. So it means we can process any sort of weird side chain that some proposer might throw at us, and particularly the one slot reorg case is now trivial because we can just, actually I've got a diagram of that. We'll almost always have sigma 1 still in memory when we get the next block, and then we just clone it, which is really cheap, and then apply the block and mutate it, and then we get the new state here, and then we can have all 3 states in our memory, and then whatever happens next, we're prepared for it because we have everything in memory. Cool. I'm just gonna have a sip of water. There are some challenges to using the tree state representation. This is actually where the name tree states comes from as well. So this is the origin. Although it's kind of overloaded to mean other things now. But yeah, there are some challenges. The iteration is slower, as I was talking about before. Memory fragmentation can be a thing, like compared to just having data in a vector where it's all in one vector and it's contiguous. We're now allocating all of these nodes everywhere, and the memory allocator has to deal with all of these tiny allocations. And then the diffs in memory, they're not diffs per se, but these new nodes that you get when you mutate a data structure, pardon me, are they can still be large. And this is something that sort of caught us off guard with Holesky, because we had the state cache size set to 128, which was very aggressive, I guess. And then in Holesky, we ended up with all of these, during the non-finality incident, we ended up with all of these very different states where the diffs were very large. And I think they were up to 200 megabytes, which is almost the size of a full beacon state. So yeah, that diff was really large because of the inactivity scores and the balances changing a lot in every epoch boundary. Basically, all the validators were getting penalized, and we were generating this like a lot of churn in the state. And so that's something that we've been working to improve. But yeah, there are also huge benefits to this paradigm, and I think on the whole, it's been worth the trade-off. So Lighthouse is now much more resilient to processing forks and reorgs. Block production is faster because you have to do this thing in block production where you want to get the current state, you want to produce your block on that state, you want to compute what the post state is, and then you have to basically throw that away and broadcast your block to the network. And then when you get the block from the network, even though it's your own block, you have to then reprocess it. At least that's how it works in Lighthouse. Maybe some other clients do a thing where they keep the post state after block processing, but that's not something that we do because it's, you have to re-execute the execution payload and stuff. So yeah. And then, this has also helped us have slightly faster API queries because anything that requests state that's cached, and we can cache so much more state, is going to be fast. So that's been really useful for like people running API servers and stuff off Lighthouse. Inspired by the Holesky non-finality incident, we have a few improvements coming up, and I'm working on a blog post to cover these. They're not actually ready yet, but hopefully soon the changes and the blog post will be ready. The main one that helped for Holesky is intra rebasing, which is the idea of reusing identical entries of a list to share memory. And I wish I had a diagram here, but you can imagine if you have a list that's all zeros, you don't actually need to have multiple copies of the zero leaf nodes. You can have this sort of circular thing where you have basically 1 0, and then you have a parent node where both its left and its right child point to that 0. And then you have another parent node where both its left and its right point to that same child node. So you can basically sort of collapse the whole tree into a pretty much a linked list where the left and the right children are the same sometimes. Or you can do things where you have, if two subtrees of nodes are the same, then you just reuse the previous subtree. And this is something that, we have a function that you give it a list, and then it looks at similarities, like sort of self similarities within that list, and then it will reduce the memory usage by taking out these subtrees that are in common. And this, I think, this dropped the memory usage for the Holesky states from about 200 megabytes to about, I think, 100, because we eliminated like a lot of duplication in the inactivity scores, which was cool. And then the other thing that we're working on, which is a bit trickier, is pruning the size of the cache, or pruning the cache based on how much memory it's currently using. So if we can measure how much RAM a particular tree or state or list is using, then when we're pruning, we can say, okay, well, give me the least useful and most memory using thing, and I will delete that first. And I think this is a really cool idea, because it means when you're running a node, particularly if you're running on like constrained hardware, say a Raspberry Pi or something, you can say, okay, I do not want to use more than 4 gigabytes of RAM, and I want you to prune the cache to stay within that limit. So that's something that we're quite excited for. It's just there's a bit of overhead to working out how much RAM one of these data structures actually uses. Remember, you have to sort of explore the tree and calculate stuff. If anyone's interested in this stuff and wants to like get involved, there's some pull requests on the Millhouse repo that you can look at. Cool. Maybe that's a good spot to pause for a quick question. Does anyone have any questions about the in-memory stuff?
Any thoughts, any questions? Yeah, Katya?
Michael, I wonder what happens when the memory is overloaded.
Yeah. So actually, that's a very good question. At the moment, it's a bit of a risk. What we do is we just hope we set the size of the cache to a specific number of states. So say 32 or 128 states, and we just hope that it won't run out of memory. Because what happens if it runs out of memory at the moment is Lighthouse will probably just get killed by the operating system for using too much memory. And that was happening quite a bit on Holesky, and that was one of the reasons we actually lowered the cache size from 128 to 32 in order to limit that. But yeah, this size-based pruning, where we can measure our own memory usage and keep it under control, is a much better solution than just setting some limit and then hoping that we don't run out of RAM. Because yeah, at the moment, the limit is just set to 32 for everyone, regardless of how much memory they have. So yeah, running out of memory is very bad. It basically it means you have to you have to crash and then you have to start again. Does that answer your question?
Yeah, and will you be slashed in this case or not?
No, you won't get slashed, because you will lose a little bit of revenue if you're running a validator. But slashing is really only for like misbehavior, where you're signing two messages that conflict. So it wouldn't cause you to do that. You would just drop offline momentarily, and you might miss a couple of attestations, and you would not get paid for those attestations. So you might get penalized a tiny bit for those attestations. But if you crash and then you come back up and you're online and you're attesting again, then you're fine. The problem with running out of memory is that often it'll just go in a cycle where you'll build up memory and then you'll run out, you'll crash, and then you'll start again. So you might attest for 5 minutes and then crash for 5 minutes, and then attest for 5 minutes and then crash for 5 minutes. So yeah, validators can go through these cycles sometimes where they're having performance issues, where they're not really, particularly if there's non-finality, they're not really making money. They're not earning any rewards. They're mostly getting penalized because they're mostly offline. And the penalties are higher when the chain is not finalizing, because it's like that's the incentive to try and kind of get back online. So yeah.
And if I've been a proposer, so they will just have a missed block.
Yeah, exactly. Yeah, if you have a proposal, like maybe your node crashes, a minute before you get the proposal, and then by the time you're back online, you've missed it. Yeah, you could miss a block like that. And yeah, a lot of the people running on Holesky were running like hundreds of thousands of validators each. So if you have 100,000 validators on a beacon node and then the beacon node goes offline, there's a good chance that you'll miss something good. But yeah, it's also just a testnet. So we're glad that that happened on a testnet and not on mainnet. And in general, yeah, testnets are always a bit bumpier than mainnet because although people are trying to keep their stuff online, they're not actually gaining and losing real money by doing so. So it's always a bit lower in terms of participation and stuff.
Thank you.
No worries. Any other questions?
Yeah, I think we are good for now.
Okay, cool. Yeah, let's go on to the disk stuff. So how do we store the state on disk? Because we've covered how we store it in memory, but if the node crashes or something and comes back, we want to still be able to pick up where we left off, basically. And in the beginning, when everyone started working on the beacon chain 6-7 years ago, the beacon state at that time was very, very small, and people were thinking about strategies like, oh, well, what if we just write the beacon state every slot? And I think Lighthouse used to do this very, very early on, like before any of the real main testnets. These days, that would be a very, very expensive way of storing state, because every state is about 250 megabytes, so you have to write 250 megabytes to your SSD every 12 seconds, which is going to wear out your SSD pretty quickly. And you would also end up storing about 657 terabytes in a year doing this. So that's crazy. That's like larger than any disk that anyone has. And it's larger than any execution node, archive node, or anything that anyone complains about having to store. So we definitely can't do this. The next simplest approach is to, okay, well, what if we don't store a beacon state every slot? What if we store one every epoch? And an epoch is this, this 32 slot period. So this is a lot better, but it's really only 32 times better. So it's 20 terabytes per year instead of 660. And it's still 250 megabytes of IO that just happens in a big burst once per epoch. And then, yeah, this is still important to think about, because we do sort of end up using an idea that's kind of like this, because we still use this concept of block replay. So if we only have every state, if we only have a state from one state from each epoch, the question is, well, how do you get to those states that are in the middle of the epoch? You might have stored the one from slot 32, but the current chain is at slot 36. So how do I get back to slot 36 after I shut down my node and start up again? And the answer to that is that you can replay the blocks. So if you've got the state at slot 32, you would apply the blocks from 33, 34, 35, 36, and then you would have the state at slot 36. And this block replay doesn't use any memory, it doesn't use any disk space, because you already have those blocks stored. But it does use some processing time to reapply those blocks. So there's a trade-off there between how much you store on disk. Do you store 657 terabytes, or do you just store the blocks and then try and replay the blocks? But if you have to replay too many blocks, like if you have to replay 100,000 of them, that's going to take a really, really long time, like probably multiple tens of minutes or hours even. So that's not always feasible. But for short distances, block replay is really useful. So if you're only replaying one epoch at a time, you can do that really quickly in probably less than 100 milliseconds. Yeah, so most beacon nodes, Lighthouse included, use a couple more optimizations on top of just replaying blocks. The main one that helps a lot is to just not store historic states. So when the chain is finalizing, there's usually only around 2 or 3 epochs worth of states that have not already been finalized. And any blocks that come in are going to have to reference those states and can't reference things that are already finalized, because the things that are finalized are already fixed. You can't build a block that builds on an old finalized state. That's just not valid. The network will reject it. So if we only have to store 2 epochs worth of states, then actually either of these strategies are fine. You could write the beacon state every slot and it wouldn't be that many, or you could write the beacon state every epoch and it also wouldn't be that many. You have between maybe two epoch boundary states, which would be 500 megabytes, or you could have 64 states and that would be 32 times larger, so it'd be like 16 gigabytes. But that's still within reasonable limits, right? If your node uses 16 gigabytes of disk, you're not too worried. It's better than using 16 gigabytes of RAM. Pardon me. But then there's also other options. So for historic states, maybe you do want to keep them around sometimes. So there's certain use cases where people want to go back and look at what the state of the chain was in the past, particularly for validated rewards analysis and things like this. So what we used to do in Lighthouse was we'd have a system where you could store one state every 8192 slots. It's this number for a very specific reason, but 8192 slots is about a day and a half or something, maybe a little less. So you would have one state every day, roughly, and you could store all the states back to 2020 without using too much disk space. This is like, I guess 8192 is, it's several times smaller than the 20 terabytes per year. It would probably end up being maybe a few hundred gigabytes max, 200 gigabytes or something. The problem with this is that replaying 8192 blocks to get to any specific state takes quite a long time. So if you have a snapshot from yesterday at 12 p.m. and then you want the state from today at 11:59 a.m., you would have to replay all of the blocks in between, probably 8,191 or 8192, and that would take potentially like up to, I think we saw it take up to like 10 minutes to get one historic state. So although you had access to all of those states, it wasn't necessarily quick access. And that was pretty useless, because usually people that are doing this sort of analysis, they want to run a whole bunch of queries against the historic state. They don't want to just load one time. So having it take 10 minutes is just not really practical. So this is where we cooked up a feature called hierarchical state diffs. And this, for a long time, this is the sort of technically correct name. But for a long time, it was bundled with the in-memory tree states feature. So this came to be known as tree states, because we had a couple of experimental test releases that we were calling tree states that had this and had the memory change. And that people didn't really notice the memory change as much as they noticed this, because people that were running archive nodes were like, wow, this database is much smaller and the queries are much quicker. So this is the tree states, and it is a tree in a way, but really the original tree states that the name is drawn from is the in-memory one. So this is the hierarchical state diff diagram that I'm going to show you, and it looks a bit crazy, but I'll explain the idea, and hopefully it makes sense. So similar to the idea of storing a beacon state and then doing block replay to get to a different state, we thought, what if we store a snapshot very, very, very infrequently? So every 2 to the 21 slots, that's about once per year. So if you have a snapshot that's once per year, and then you have a diff from that snapshot to each month of the year, say, so you have a January, February, March, April, May diff, then you can just jump to any month by applying that diff on top of the yearly snapshot. So you, to get the state for, say, April 1st or whatever, you would load the snapshot for that year, for this year. Then you would load the April diff. You'd apply the April diff on top of the snapshot, and that would take you to probably April 1st because it's the first day. But say if you wanted April 4th, then we have another layer in the tree, which you could think of as like the days of the month, and these are diffs with respect to the start of the month. So to jump to April 15, you would grab the one for April 15 and apply that diff on top of the April diff, which you'd already applied on top of the snapshot, and then you have the state for April 15. And yeah, that's kind of the concept behind hierarchical state diffs. We call them hierarchical because they are sort of organized in this like top-down or bottom-up sort of chronological structure. And yeah, we actually, I think we have 6 or 7 layers by default. So the layers that we have don't quite correspond to years, months, days, but it's more or less that kind of thing. So yeah, if you want a specific state, you'll probably jump back in time along a couple of these, like these diff edges to load your state. And then we also still support block replay at the leaf level. So I think the default configuration, it will use diffs to get a state that's on an epoch boundary. But then for any states that are more granular than that, so like in the middle of an epoch somewhere, we will just replay the blocks to get to there. So we still have this property that we're only ever replaying at most 32 blocks. But yeah, we have this very quick, this diff thing to load, however many layers there are. In this case, there's 4. You would load at most 4 diffs and apply those. So yeah, that's hierarchical state diffs. We released that in Lighthouse in version 6, which went out in December 2024, which is just a couple of months ago. This results in us being able to store all the states since 2020 in 163 gigabytes. I checked my node yesterday, and that's how much it was using. And the cool thing about this is this 163 gigabytes is with the default configuration of the layers, but you can also completely configure how dense you want your diffs to be. So if you want to have less layers of diffs, where each diff is a little bit chunkier, you can do that. If you want to have more layers of diffs, you can do that. If you want to have less frequent snapshots, you can do that. If you want to have really frequent snapshots so that you can jump to anywhere quite quickly, you can also do that. And you can really trade off disk usage against performance. There's a huge state space that we haven't even fully explored of these like diff configurations. We've found one that we think is pretty good, but there could be a better one out there. Like if we had a lot of time, we could sync 1,000 nodes with 1,000 different configurations and then see which one is the best. But that would use like a lot of disk space and a lot of time to sync them. The specifics of the diff algorithm that we're using at the moment are that we split up the diffs for the balances and the inactivity scores because they're often repetitive and often changing in very similar ways. And we split them off from the rest of the state. Mainly the validator registry is the thing that uses a lot of space. So for these balances and inactivity scores, because they're just vectors of numbers, what we do is we just go along the vector and we subtract the old value from the current value. So it's just like the new value minus the old value. So if your balance changes by 1, +1, then the diff will be +1. If it changes by -1, then the diff will be -1. And then that gives us this vector of differences, basically, which are probably quite repetitive because balances change in similar ways for validators. Like if everyone's getting the same reward, then this vector is just going to be the same number over and over again. And then we run that through a compression algorithm, Z standard. This is one, I think Facebook developed it or something, but it's kind of like, it's a really good, when we did benchmarks, it's a really good compression algorithm. It compresses data like quite a lot and also very quickly. So that's really cool. And then we have, this other one is less well known. The diff algorithm that we use for the rest of the state is called X delta 3. It's just a C library that was written by some guy, as far as I can tell. But it's kind of, it's used in some Unix projects, and it's not like completely Wild West sort of code. So it's relatively stable. It's just not being updated anymore. But it was the best when we benchmarked both the compression ratio and the speed of compressing and decompressing. It was by far it met the sort of sweet spot for being quite compact, but also quite quick to compress and decompress. So yeah, that's what we've used at the moment for the validators. But yeah, we are open to changing this so that the diffs are versioned on disk. So in the future, we could potentially change algorithms, and it would be completely backwards compatible, because we could continue using the old diff algorithm for the old disks that people already have, diffs that people already have stored, while storing new data with some new algorithm if we wanted to. We've actually recently worked out a small change that we want to make to the diff algorithm, and we're going to do that using a schema upgrade that will go through and then hopefully just be completely transparent for users. Yeah. So the freezer state hierarchical state diffs are very useful for the chain when it's running normally, and if you want to keep all of those historical states, it's really great. I think it's probably it's probably the best way to store archive states. I think there's a couple of other clients that are working on this now as well. I know that the Aragon consensus client called Kaplan have something that they claim is even quicker than our thing, and I think they're probably right. But yeah, there's maybe a bit of more optimization to do there. But the main downside is that we can't use this hierarchical state diff system at the moment for the non-finalized states, because it only works for those historic states in the freezer database. So during the non-finality incident on Holesky, and we knew this was a problem, so this was something that we were preparing for, but we got caught off guard, basically. But yeah, during that non-finality incident, we ended up using a lot of disk space, because Lighthouse's strategy for the non-finalized part of the chain is still to just store a state every epoch. And when finality stops, you end up storing, I think we had 3 weeks of non-finality. So we had, whatever, 225 times 3 weeks. So it's 225 epochs in a day, times 21 times 250 megabytes per state. So the disk usage was growing at a really alarming rate. And then also we have every side chain also has states stored on it. And they were also using a lot of disk space. So I think Lighthouse on Holesky was using upwards of 700 gigabytes, 800 gigabytes, more than a terabyte sometimes, which is like really, really, really too much, and can potentially lead to, this sort of death spiral where the network, it like runs out of space, and then people get knocked offline, and then because they're offline, more people run out of space because the chain is still not finalizing. And it's kind of this, like, once the chain stops finalizing, it can be really hard to get it back. We did manage to get it back on Holesky, but through sort of sheer willpower and like getting people to coordinate in a really I guess, an unusual way that they probably wouldn't coordinate on mainnet. People basically agreed to slash themselves, which is, would not happen on mainnet. But yeah, we do have a plan to fix this, and this was something that we were working on even before the Haleski non-finality, and it's to use the hierarchical state diffs for the non-finalized states too. This seems to work really well. It's just in the process of being tested, and we're ironing out a couple of bugs and making sure that it's really like watertight before we ship it on mainnet. Yeah, behind the scenes, something that I've sort of glossed over is how is this data actually getting stored in the database? Most clients use an embedded database of sorts, so either LevelDB, RocksDB, MDBX, RedDB, sometimes SQLite. I think Nimbus might be the only one using SQLite. And yeah, these databases are basically used as like a key value database. So you have a key that is some bytes, and then you map it to a value, which is some other bytes, and the database just stores those for you, and you can then look them up later. All of these databases support some form of like transaction or an atomic write. The one that we use in Lighthouse mostly is LevelDB, and it's looking a bit old at this point because it doesn't really have proper transactions, but it gets the job done for us, and we will probably move to RedDB as it becomes more mature. RedDB is like it's a Rust embedded database. Yeah, this is the last section, and then maybe we'll do some more questions. So there's a bunch of other data apart from the state that we have to store, namely the blocks and the blobs are very important, and the way that we store them in Lighthouse is actually pretty straightforward. And we probably want to change both of these strategies in future, but at the moment, the way blocks are stored, we just use the block root as the key, and then we have the SSZ block as the value. So this is just the block root maps onto the bytes of the block, and then when you want to look it up, you give the database the block root and you say, hey, give me the data for this block root, and the database just gives you the block straight away. It's very simple. The downside of that is that we actually store all of the blocks that we have in the database in one big bucket. So the things in there are moving around a lot because they're just ordered by block root, and then the database will like rebalance those every now and then. So an improvement in the future that we want to do is to actually store the finalized blocks by their slot as the key, because then that allows us to store them sort of in a contiguous in a block. So sorry, not in a block, in like a sequence. So if you want to load all of the blocks between slot 0 and slot 1000, you can just go to the database and go, okay, 0 to 1000, they're all sitting there next to each other, and I can just load them all up really quickly, and there's no like fragmentation happening. Whereas at the moment, if you want to load 0 to 1000, you have to go, okay, well, 0 has this block root, and then 1 has this block root, and you're like jumping around everywhere. There's a lot of non-local accesses. And then, yeah, for blobs, it's very similar. We use the block root as the key because blobs are fundamentally always tied to some block root. And then we have an SSZ list of blobs as the value. And honestly, this was a mistake. We should never have stored the full list of blobs as the value. What we should have done was use the block root as the key and the blob index with it also as the key, and then have a single blob as the value. So then that would allow us to say, okay, I want blob 1 from this block root. So you'd say the block root and then 1 as the index, and then you would get a single blob. And you would still be able to iterate all of the blobs for a block root by just looking up the block root and index 0, and then looking in the database, because everything in the database is stored in like key increasing order. So if you have block root 0, block root 1, block root 2, block root 3, block root 4, they are all right next to each other, and you can always get the list from the sort of keyed form, whereas you can't go the other way. So the advantage of the system that we want to move to is that it would allow us to store just a subset of the blobs for a specific block. A lot of the layer 2s are not really interested in all of the blobs ever. They only want to know about the ones that are related to their layer 2 sequencer. And yeah, this is something that we want to support long term, where you can have a node that just knows a subset of the blobs. Yeah, I've put some links here. These are kind of adapted from a previous talk I did on that was more on the functional data structure side. But if you're interested in digging into the ideas behind Millhouse, I've got some links for functional data structures and functional programming generally. There's a library that we do also use that I didn't really cover called Rapids, which is persistent data structures in Rust. If you're familiar with Rust, that might be interesting. Proto Lambda, who works at Optimism now, but used to work on L1, also has a Python library, which was a bit of an inspiration for Millhouse, which is our library. This works in a very similar way, but just adapted to Python. And then, yeah, we've got the Millhouse library. And if you want to learn more about the Lighthouse tree states on disk, then we have docs about that in the Lighthouse book. Thank you. Any questions?
Awesome. Yeah, thank you very much, Michael. Yeah, we have a hand up from Katya. Yeah.
I wonder, do you have any improvements, these strategies for storing blobs, and I mean the same as for beacon state?
Oh yeah, so blobs are hard, right? Because they don't have a lot of structure that we can exploit. Like the beacon state, the diff thing works very well because it's always like evolving from a previous version of itself. Whereas blobs are kind of just random, right? Like or maybe some of them could be related to each other, but often from the beacon node's point of view, it's just like, here's some arbitrary data that you have to store. Yeah, a while ago we were thinking about trying to use compression just on an individual blob basis. Just if there's repetitive parts within a blob, you could at least compress it a little bit. Or I think sometimes blobs will have a lot of zeros because they're like filling out to the size of the blob, because blobs are fixed size, right? So we could potentially do compression. That might be something that we do when we do this transition. But yeah, I think with PeerDAS, when we have data columns, I think because they're encoded in a way, they use like a redundancy coding. I don't think they will compress very well. So yeah, I'm not sure. Do you have any ideas for blobs?
No.
Yeah, it's hard. I think no one really has any ideas for how to compress blobs. I think one of the things that maybe helps for blobs is having just better tooling for controlling which blobs you want to store and being able to import and export them from nodes and stuff. So this is something we're working on at the moment, and we're planning to host like we're going to try and host an archive of all the blobs on mainnet, because this is something that no one else really seems to be doing. I remember there's a few people that have this, but we want to host that and then encourage other people to seed that data, and then from there maybe people could build specific snapshots, like, okay, here's all the Optimism blobs, or here's all of the blobs for a different L2, and then yeah, that could be a way of like keeping the storage manageable.
Yeah, thank you. You should reach out to Mario. He likes archive nodes.
Yeah, if you want to host one, let me know.
Well, I'm running my Erigon archive node right here, like next to me, and I ran out of space with Lighthouse a couple times already, so I switched to Kaplan for now.
Oh, interesting.
It was,
Okay.
it was actually getting like it was always getting too big, and I cared more about the execution archive. So I just resync it from checkpoint every time, and now I don't have any Lighthouse archive data anymore. But Yeah, maybe if I get another disk.
Yeah. So you were running it with the tree states database, and it was still too big?
Yeah, so it was the after the update it got better, but it was still running out of space. Like it was just growing so fast. Like I'm not sure. Yeah, even if I resynced from checkpoint, after a couple of
Mhm.
weeks it was like a terabyte or something. All of a
Oh,
sudden.
really?
Yeah,
Oh,
yeah, yeah. Maybe it was just my settings or something. But so actually now the new version of Aragon is smaller. I need to resync the Aragon because they have the Aragon 3, which is like
yeah.
1 terabyte smaller. So I might be able to try it again. So I'll give it a try with the
Yeah, okay.
refresh settings as well.
Yeah, I don't think Lighthouse should ever hit a terabyte anymore, with the default config anyway. But we can chat about this.
Yeah, totally. Yeah. Yeah. Need to try it again. Like I would like to have both archives, but yeah, so far I could fit only one. Yeah. Cool. There are some questions in comments. Maybe if you can see them in the Jitsi, you can read it. There is a
Oh yeah.
question on SSZ. Uh,
Um, in the Jitsi, I don't see
can,
it here.
can you see it in comments or?
I
I
can only see
also, the
people saying
comments
hello.
aren't really working for me either.
Oh, that's weird.
It
Yeah, I
stops
had
like
I
right
had
after I'll grab coffee.
yeah. I had some of them disappear. It's weird. But there is a question. Can you talk more about SSZ and how the I'm not gonna pronounce it. Merkel is fucking like
Merkleization.
macrolization works. Is it similar to immutable vectors you talked about before?
Yeah. So SSZ and Merkleization are two things that we do with the data structure once we have it in memory. So the SSZ representation is basically it's like a flat representation of all of the data in the data structure. And to encode as SSZ, we have a function that can basically encode a list by just iterating along the list and just writing out each entry of the list. So when we're doing SSZ, we iterate along the leaves of the tree, and we leave out all of the internal nodes, which are only related to Merkleization. And then that gives us basically it's fairly similar to a flat vector of the leaves. And then obviously if the leaf nodes themselves implement SSZ, they will get serialized inside the leaves. And SSZ has some stuff. The quirkiest thing about SSZ is it has some stuff about what to do for things that are variable sized versus fixed size. So when things are fixed size, it's all fairly simple. They just get written out. But when they're variable sized, they'll get written in a different place with an offset that tells you where they're written. So yeah, SSZ. We have in Lighthouse, we have a derive macro that implements SSZ encode and decode for any struct. And then it's just the basic types like numbers and lists that we have to implement SSZ manually for. And then the derive macro, if you have a bunch of, like the beacon state has a bunch of fields that are U64s or lists or whatever, they're the sort of primitive types. The derive macro completely takes care of that and just says, okay, serialize each of these fields in order. And then when you're deserializing, the same thing, just deserialize each one. And then that will use under the hood the basic implementations. I hope that answers the question. SSZ is one of those things that sort of, it has a bunch of subtlety, but you just look at the spec and you just try and do what the spec is saying and run some tests and make sure that it's working. It's not, I would say it's not especially complicated, like on a conceptual level. It's just a binary format. For Merkleization, we actually leaned more into that with the immutable list thing. So Merkleization is the process of hashing all of the leaves into the internal nodes, and all the way up to the root. And we are storing all of the hashes inside the immutable vector tree. So we are caching all of the hashes that we want to have. So This means that hashing is very fast for the Millhouse types because we have a full cache of all of the hashes for the previous nodes. And then when we apply a mutation, we might get some new nodes that aren't hashed yet. And then when we rehash the tree, we just rehash the parts that are new, and we reuse all of the hashes that we have for the parts that are already hashed. So yeah, our benchmarks for like hashing the beacon state got a lot faster when we switched to the Millhouse type, because we were not redoing as much work, and we were able to take advantage of the similarity between each successive state.
Very well, thank you so much. Awesome. Any more questions? Feel free to raise your hand. We have some that we missed in the comments before. So I'm not sure if it's still was answered, but do these data structures apply to every client?
Yeah, so every client will be using some variant on these data structures. The ones that I've described are somewhat Lighthouse specific. So the hierarchical state diffs are pretty Lighthouse specific for the database on disk. I don't think anyone else is doing it exactly like we're doing. Kaplan is probably the closest, but I don't actually exactly know what they're doing. And then the in-memory one, yeah, the in-memory tree states are used by, I think, at least Lodestar and Grandine, maybe Peku, but I actually don't think Peku do. Yeah, so Lodestar has a very similar system to us, where they have these consistent trees that are mutable and the copying. And Grandine too, as far as I'm aware. So yeah, and then a lot of the other clients will have similar sort of tree structures. Like what we had in Lighthouse before we had this was a sort of more customized cache that was just for the tree hashing, the Merkleization part of the calculation, and then the actual data was stored in a vector. So a lot of the clients are using something like that, where they do have a tree, but they keep the tree separate from the data. Whereas we've decided to put the data and the tree together in one thing so that it's all unified. And both of these have their advantages and disadvantages. We've leaned into being able to copy the data is a useful thing. So being able to clone it and make variants of it really cheaply, we think that's a good thing. But if you just want to have really, really fast updates, then it's actually going to be quicker if you have just a regular vector that you can update, and then a tree that you keep separately. So there's pros and cons to each, and different clients do slightly different things.
Interesting. Thank you so much, Michael. Yeah, very well. Right. Folks, any more questions? Feel free to ask. Raise your hand. We have some that we missed in the chat because of the mess, so feel free to repeat them. Yeah, Tiro?
Yeah, hey. I was wondering how you guys are thinking about implementing the pruning feature.
Oh yeah. It depends what you mean by pruning. So there's several types of pruning. Do you mean the like EIP 444 where we drop history?
I'm thinking of if you could open up the slides.
Yeah. Well, hang on. Give me a sec. Can you see my screen now? Yeah. Sorry, you still there? Can you hear me?
Yes, I'm here. Sorry.
Which slide?
Go on. Next. It's about the state. Yes, up. Again, I think.
This one?
No.
This one.
Next. Next. Am I sure about where?
Oh, you mean
Yes.
the one about storing states during non-finality?
Exactly. Yeah.
Yeah. So what we're doing for this is very similar to the hierarchical state diff algorithm. The thing that's different is for historic states, it's all very simple because there's only ever one state at a given slot. So the sort of all the indexing and all the math that we do is just related to the slot for the historic states. So that's like quite simple and easy to understand. In the case where the chain is not finalized, you have to deal with multiple forks. Like during the Holesky non-finality incident, at one point there were more than 1,000 different forks, 1,000 different potential head blocks. And ideally, we want to be able to store all of the state for all of those forks, which is kind of a lot of state. So we still use the same idea of the hierarchical state diff. So we have like the yearly snapshot, the monthly snapshot, the daily snapshot, the daily diff. So yearly snapshot and then monthly diff, daily diff, whatever. But we have those tied to a specific chain. So we might have multiple diffs for, say, April 3rd. And then, the two diffs for April 3rd might point to the same diff for April 1st, or they might point to different ones again. And then they might point to the same snapshot for the start of the year, or they might point to different snapshots for the start of the year, depending on how long non-finality has been going. But most of the time, non-finality is relatively short. So the length of these diff chains will be relatively small. And there's just some complexity around how we store the finalized state itself, because the finalized state is a sort of natural snapshot for the diff algorithm, but it's always moving. So you don't want to diff. You don't want to diff with respect to something, and then your thing that you're diffed with respect to moves forward, and then the thing that you were diffing from is now deleted. So we are dealing with that by also keeping some of the older state that is an ancestor of the finalized state. So we kind of have like another diff snapshot in the database, say from the start of the year, which acts as the basis for the finalized state and everything after it. And then that snapshot gets used. Despite being older than the actual finalized state, if that makes sense. That probably doesn't make sense. I think I'm not explaining that particularly well. But yeah, to summarize, the idea is that we use the hierarchical state diff thing, and then we tag each of those chains of diffs by the state root of the chain. So we can have multiple diffs at the same slot.
Wouldn't that like have a big overhead for like memory and storage as well?
Yes, it does. It's definitely more than the freezer database, but it's still a lot less than storing the state every epoch, because the diffs are relatively small. Like a lot of the diffs are, a megabyte or less. So even if you have 1,000 diffs for slot, 10 slots after the finalized state, that's still a lot better than having 1,000 times full states at that height, if that makes sense. Like you'd have 1 megabyte times 1,000 rather than 250 megabytes times 1,000, which would be the current system.
Makes perfect sense. Thanks.
No worries.
Yeah, very well. Any other questions, thoughts? We still have a few minutes to go. If you guys want to use them, please go ahead. Um, or again, if we missed any of your questions in the comments before, I'm very sorry. Feel free to repeat them. Okay. Yeah.
I wonder how you use cache for this strategy. Like,
Yeah, actually, that's something I didn't cover, but we have a so for the do you mean more for the hot for the non-finalized states or more for the freezer states?
for
I can
freezer
cover
states. Yeah.
for freezer, yeah. So I can cover both if you like, but I'll cover freezer first. So yeah, we have quite a complicated, or let's say complex cache, because there's two ways of storing those historic states. They can either be as like the bytes that you get out of the diff algorithm, or they can be as like the deserialized tree, basically in memory, like a Millhouse tree. So the cache actually uses both of these representations, and it will convert between them like sort of on demand. So if say if you load the state at slot 1023, how that will happen is you'll load the snapshot, you'll apply a bunch of diffs, you'll get the slot 123 state, and you'll convert it from bytes into a full state. And then that full state will get served back to the application layer. And then if you request the state at slot 1024, we will look at the cache and we'll say, okay, well, we have the diff bytes for 1023, and we also have the full state for 1023. And we could use either of these to get to 1024. So what we'll do is sort of opportunistically, if we have the state there, then we might just replay one block to get to 1024, and then we have the state for 1024. Or if it's like a longer distance, say we had the state for 1023, and then we load like 2048, and 2048 is diffed off. It would probably be more likely to be diffed off 1024. So say we have the diff bytes for 1024 in memory, and we load 2048. Then we would have the diff bytes for 1024, which is just a bunch of bytes, a vector, and we would load the diff for 1024, diff for 2048, and apply it on top of those bytes to get the bytes for 2048. So we do this sort of combination of keeping the bytes around, or keeping the state around, or sometimes both. And there are probably still improvements that we could make to that cache, but yeah, the one that we have at the moment is potentially it could be a bit inefficient, because sometimes it will miss an opportunity to or it might just store too much, I think, because it would be maybe storing the bytes and the diff, or it would miss an opportunity to like to use some information that it already has loaded. Yeah, does that answer your question?
And yeah, and for non-finality?
And then for non-finality, it's a little bit simpler. We just store a bunch of states in memory, and then we rely on the sharing between the nodes of those states. So we have like the finalized state, and then usually with 32 states cached, you'll have the finalized state, you'll have and all of the states in the most recent epoch, and they're all sort of sharing a lot of their data in common because of the fact that they're based on each other. We also have an operation called rebase, where you can take a state and you can make it share as much memory as possible with another state by wherever they have identical data, you use the data from the base state. So something that we do with the state caches, we often, if we get a new state, we'll rebase it on the finalized state so that it's sharing as much as possible with that finalized state. And then we'll put it in the cache. But yeah, that's the cache. That state cache in memory is the one that we want to implement the size-based pruning for. So the one where we want to say, okay, I only have 8 gigabytes of RAM, or I only have 4 gigabytes of RAM. Do not use more than this. And then it will prune states from there based on how big they are and try to stay within that limit.
Thank you.
Thank you.
Very well. Yeah, I think we are close to wrapping up. Folks, anything else you would like to ask before we finish? Any last thoughts? I think we covered a lot today.
Yeah, that actually, it went quick from my perspective, but I yeah, I feel like we did cover a lot. Thank you so much for having letting booked out.
Yeah, thank you so much for joining. Yeah, I really appreciate it. I think we have great content here that we can share, and hopefully people will enjoy the recording as much. Yeah, awesome. Yeah, thank you so much, Michael. And yeah, it was great. I mean, almost 90 minutes, so strong start in the morning for you. Yeah, very well.
Yep, cool. Thank you so much.
Awesome.
All right.
And have a great day. Bye, everyone.
You too. Bye, everyone.